There's one more topic we're going to cover in this chapter, and that is complex ion equilibrium. We're not going to cover it in super great detail, but I think you should be aware of complex ions and the fact that there's an equilibria involved with them as well. And so a complex ion is an ion that contains a central metal cation, because those are going to be cationic, and then there's one or more molecules or ions that are bonded to that, and that is the complex ion that we're looking at. It's still ionic, and so we're not talking about something that's a solid. We're talking about these ions that are bonded to that metal ion, and then they're still floating around in solution that way. So when we talk about these, we can think about their formation as looking something like this, where we take a cobalt ion here, so cobalt 2 plus, we would have 4 chloride ions that it would react with, and then we would have that in equilibrium with the complex ion. And so this over here is our complex ions. This is a cobalt ion with 4 chloride ions with it. Notice it's still ionic, right? We have 2 plus ion from the cobalt. Each of those chlorides brings a -1, and so our total on this complex ion is actually a -2 charge. And so it's still ionic, it's still floating around in solution. A couple of things to note. Remember that when we write something like this, so cobalt 2 plus, aqueous, I should say, that's kind of a misnomer. It's not really what's happening. Remember from back in lab and when we talked about this with some acidic solutions from different ionic compounds, that really this is not a thing, right? We don't have a cobalt 2 plus ion floating around in solution by itself. In fact, that cobalt is actually surrounded by a number of water molecules. And so this is a shorthand that we write, so we don't have to write those water molecules in all the time. But anytime you see one of these metal cations with an aqueous next to it, remember there are some water molecules that are associated to that cobalt ion. And so really this equilibrium that we're looking at is kind of a competition between the water molecules being attracted to the cobalt ion and these chloride ions being attracted to the cobalt ion. And so you have an equilibrium back and forth where sometimes you have water molecules associated with the cobalt, and on the right-hand side you have chloride ions associated with the cobalt. But this is how we would write a formation reaction for one of these metal complex ions. And so the formation constant is sometimes referred to as the stability constant because it basically gives us a comparison of how stable this particular ion is compared to, say, the water version of it or the cobalt by itself. Okay, so we call it Kf. It's the equilibrium constant for this kind of formation of a complex ion. For this particular reaction, we would have the concentration of that complex ion over the concentration of our cobalt and the concentration of the chloride raised to the 4th power. And again, those powers are just coming from our stoichiometric coefficients. You're always going to have a 1 in front of the thing that you're forming because this is a formation reaction. And so you might have, you're generally going to have a 1 in front of your metal ion as well, because there's going to be one central metal ion. Really the thing that changes is how many of those other ions are bound to it. And so you might have 4, you might have 6 in some cases, things like that. So this is our formation constant. And as you can probably guess, as the formation constant goes up, if we're comparing different constants, the larger the formation constant is, the more stable that complex is, right? Because if I have a large Kf, that means I'm going to have mostly products in solution or more products in solution if I'm comparing two things. If I have a smaller Kf, that means I'm going to have a little bit more of the reactants than I would have products necessarily if we're comparing various things. And so if we take a look at what this would actually look like, for this particular reaction, the cobalt 2 plus, when it's the aquo complex, when it has the water molecules bound to it, is a pink color. And if you were to add some chloride to that solution, that would go towards the chloride complex ion, and you would have a blue solution instead. And so depending on your complex ion, you frequently actually do see these color changes because complex ions have some really interesting colors depending on what the central metal atom actually is, or the cation, I should say. Okay, so let's look at just a sort of really qualitative kind of example, and that's as much as we're going to deal with this year. Is we're going to deal with just the qualitative of this, not so much looking at the equilibrium from a quantitative perspective. But let's say we have a solution in which we have some silver ion, we have some ammonia, and we have some cyanide in the solution. And the question is, which complex ion are we going to form? Or are we just going to leave this in the aquo form where the silver just has some water molecules associated with it? And so if we take a look at the complex ion formation reactions, so if I have silver ion, two ammonias can associate with that silver ion. Notice because there's no charge on the ammonia, it doesn't actually change the charge of my ion here, so it's going to stay a +1. And the formation constant for that is 10 to the 7th. So that's a big number, right? What that tells me is if I have silver ion in solution and ammonia in solution, I'm going to get the ammonia complex, right? I'm not going to stay in the aqueous form. If I don't have any ammonia, I'm going to stay in the aqueous form. But as soon as I add ammonia to that, it's going to drive that to the product side. That's a pretty big number. And so I'm going to have that complex ion. If I look at the cyanide complex ion, I've got the silver with the cyanide here. Now notice what happens. I've got 2 negatively charged cyanides and my 1 positively charged silver. And so my overall charge for this complex ion is going to be a negative here. Now the constant for that is an even larger number, right? And so we're looking at 10 to the 21st here. We can compare these on equal footing because in both cases we're associating 2 things to our silver, so our stoichiometry is really the same. And so it's really just a comparison of those KFs. The KF of the cyanide complex ion is significantly larger than the KF of the ammonia complex ion. And so if I have these 3 things in solution, it's really this ion that's going to form. I'm not going to have the aqueous, I'm not going to have the ammonia complex, I'm going to have the cyanide complex. And so that's the one that I can qualitatively say is going to form in this case. There's one other thing to talk about here. We can also sometimes refer to the dissociation constant. So if I have this complex ion in solution, I could think about the opposite reaction where these things are dissociating. And this is really just the flip of the formation, right? And so if I think about the dissociation constant, or Kd, it's really just going to be the inverse of that formation because our reaction is the opposite. If we had a delta H, we'd put a negative sign in front of it, but since we're talking about an equilibrium constant, that becomes an inverse, right? And so the Kd is just the inverse of the Kf.